Okay, today we're going to talk about force and acceleration and how those two properties apply to circular motion. So, if you recall, in a previous lesson, we talked about the linear properties that we've learned before: displacement, velocity, acceleration, and force. Those are all linear properties. They are things that we have learned can be measured and can be illustrated as straight line properties. So if we draw vector arrows to represent the direction of our force, or our acceleration, or velocity, those are all straight line arrows. So we call them linear properties. But now that we're talking about things going in a circle, we need to talk about motion along a curved path, because that's what circular motion is. And so we learned that there were some new properties that had the word angular attached to them. So around the circle, along the curved path, will be described as angular properties. So we learned that we can have angular velocity and we can have angular displacement, which is going around the circle. But with that circular motion, we still have those linear properties. We've already talked about linear velocity as being the velocity at which our object would exit the circle. Remember that all objects have inertia, which says that they want to continue their motion at the same speed on the same path in a straight line. So even though we are pulling things in a circle, it still wants to move at a constant speed and direction. And so our linear velocity was demonstrating that path of inertia, how it would leave the circle. So what we're going to talk about today is, why does the object continue turning in a circle even though we know inertia says it wants to move on a straight line path? And so that's where our force and acceleration come into play. The word acceleration, if you recall, means a change in velocity over time. So we are going to continue talking about objects where the velocity is changing, and just like previous conversations, it could be a change in speed or it could be a change in direction. Now, we've already defined uniform circular motion as objects that are moving at a constant speed around the circle, but the velocity for that object, the linear velocity, is changing because the direction of that vector arrow has to change as it moves to different locations of the circle. So by definition, my object is experiencing an acceleration because the velocity is changing. If my object goes around and around and around in this circle, the linear or tangent velocity is going to point different directions at different moments along the object's path as it makes that circle. So you can see that the object experiences an acceleration because acceleration is a change in velocity over time, right? So what we are saying here is that we have a new vocabulary word. This word centripetal means center seeking or center pointing. So any word that we see or say that has centripetal in front of it means it's just going to be directed towards the center of the circle. So if we look at this picture below, here is the middle of my circle. So my acceleration is this vector right here. Acceleration is a straight line property, so it's a straight arrow, but it's going to point to the middle of that circle. That's what centripetal acceleration means. So in order for my object to move in a circle, it must experience an acceleration that directs it towards the center of the circle. So if we were to think about my object, it wants to move along this path because of inertia. Let me change that here. It wants to move on this straight line path because of the object's inertia. That's the linear or tangent velocity. But the object does not continue on that path because it gets accelerated towards the center of the circle. So instead of my object being located out here, the object gets accelerated so that it turns and moves back towards the center of the circle. So now my object wants to follow this straight line path. That would be its linear or tangent velocity at this moment. But once again, the object does not end up out here because it does not follow its path of inertia. Instead, it is accelerated. The direction of that linear velocity has been altered, so it is now directed towards the center of the circle, and so instead my object follows a path that puts it here at this moment. Okay, so this is what we mean when we say centripetal acceleration. We're taking our understanding of the word acceleration, change in velocity over time, which could be a change in speed or a change in direction. In this case, it's a change in direction, and that object is going to be accelerated so that the direction changes, which causes the object to move towards the center of the circle. Okay? Now, you should already know that all objects experience a change in its motion because it was acted upon by an unbalanced force. And so we're going to also talk about forces and how those forces cause the accelerations in just a moment. First, we're going to get our new formula for the day, or our first formula for the day. This says A equals V squared over R. So if you notice in the formula, this says AC. Now, when this formula is provided for you on a formula list, it will just say A sometimes. Sometimes it will say AC. It just kind of depends on where that formula comes from. This value for velocity is represented with a V. So remember, straight line linear velocity is going to be the regular letter V. If you are having some trouble remembering which symbol is for angular velocity and which symbol is for linear velocity, remember we use straight lines to make that letter V for our straight line velocity. Okay, I know it's a little corny, but as long as you remember what's what. Now, this is our velocity measured in meters per second. So whatever that value is, we are going to take that value and we are going to square it. Now, just so you know, we could see A equals V squared over R. And that's most often how I like to write it for my students, because I've found over the years that students get confused with too many extra subscripts. Unfortunately, a lot of students just have difficulty comprehending that subscripts are there to give specific detail about the individual variable, and kids start thinking that it means that they have to include some additional number because they're not recognizing the difference between a variable and the subscript attached to the variable. But when we see that subscript C, remember that means centripetal, which means center seeking or pointing towards the center of the circle. And some places will put a subscript T for our linear velocity. Now, I've been using the phrase linear velocity quite a bit, but if you notice, I've repeated myself using the word tangent velocity. So if you see the equation written with a VT, that's a subscript T because of the word tangent, and we defined what a tangent line was to a circle in a previous lesson, but this is just showing that linear tangent velocity, the path of inertia, the path at which the velocity would exit, the object would exit the circle if it were to leave the circle and not continue all around that circular path, okay? So don't get confused if you see it written as a V squared or if you see it written as VT squared. It represents the same variable. And then the letter R is going to represent our radius. And so again, we've defined what the radius is in a previous lesson, but let's just make sure that we are all clear. If I have a circle and here's the center of the circle, remember we will also call that the axis of rotation. So the distance from the center of the circle to the edge of the circle is going to be our radius, and that's measured in meters. Remember that if you are given the distance all the way across the circle, that is going to be your diameter, and you would have to take that number and cut it in half. So make sure that you are fully understanding what these variables represent. All right, so as I stated just a moment ago, we know that forces are what cause objects to experience change in motion. So we learned this in our Newton's laws, that force creates acceleration. Specifically, unbalanced forces create acceleration. In this class, we are not going to have to deal with calculating the net force for our situations. We are just going to tell you, here is the force that causes the object to accelerate. If we ask you to calculate the force, you are going to just calculate what that force value is. It would technically be a net force that causes the acceleration, but we're not going to have you draw free body diagrams in here. You're not going to have to account for the different forces in this class, but please understand that it is technically an unbalanced force that would cause our object to experience an acceleration. Always, always. So in this class, we are just going to simply refer to that net force or that unbalanced force that creates circular motion as centripetal force. So again, we've already talked about the word centripetal. Centripetal, once again, means center seeking. So it's going to be directed towards the center of the circle, just like our conversation with our acceleration. So you can see on the illustration here, we have our object. Inertia wants that object to leave the circle and follow that straight line path at a constant speed, but there must be some type of force that is pulling on the object that causes it to experience an acceleration towards the center. So this force is also going to be referred to as a centripetal force because that force will pull towards the center every single time. A clarifying statement here. Forces do not have to originate from the center of the circle. So if we look at our examples that we had on our opening slide of this lesson, here I have an object that is being pulled by a string, and the string is originating from the center of the circle, and so this tension force would serve as our centripetal force, similar to me twirling the wiffle ball in the classroom or you twirling your ID at the end of your lanyard. But we talked about a situation where there were some boys on a merry-go-round. It's a different style of merry-go-round than what we see in this picture. But if you recall the video of the boys that were on the merry-go-round where there was a bar that went around the outside of the circle so that the bar pushed inward on the boy's back and caused him to spin in a circle, as long as he was in front of the bar anyway. So that it served as our centripetal force. So in this case, the force came from the outside of the object, but the direction of the force was still oriented towards the inside of the circle or the center of the circle. Here we have an example of a satellite that is in orbit. So our satellite is the object that is going around the circle. Gravity pulls everything towards the center of the circle, and we've talked about gravity in the last couple of chapters. And so we know that gravity is always towards the center of the circle. So in this case, there's actually not a physical attachment. But if we think about the direction that the force is pointing, that force is pointing towards the center of the circular pattern that the satellite is going to experience. So this would serve as our centripetal force. Okay, so as long as we understand that centripetal force is center seeking, it is always towards the center. Our force is still going to be measured in newtons. Here are just some other examples, but I feel like I've done enough with that previous slide, so we'll keep going. Force is still going to be mass times acceleration. We want our force as a capital F in newtons. We want our mass in kilograms. So if it's not in kilograms, make sure you convert it. And then our acceleration, we already reviewed today, is still going to be meters per second squared. If I wanted to, I could write this as an FC. We've talked about having subscripts for our forces. We have lots of different forces that we talked about in the previous chapter. We had a list of forces, and all we did was change the letter of the subscript. So once again, subscripts give us the details for that particular type of variable. So if we see an FC, C stands for centripetal. These are things that are going in a circle, and so this specifically is the force pointing towards the center of the circle, which in this case serves as the net force that causes the object to accelerate. I could also add that subscript C. Now here is something really important that I want you to understand, especially for test purposes. It could be a conceptual question. It could be us labeling diagrams so that we are identifying where the different variables are for our circular motion on an image. Anytime we have centripetal force, we have to have centripetal acceleration. The force creates the acceleration. So whatever direction the force is pointing, that is the net force, that is the direction of the acceleration. So we talked about this in class. We talked about free body diagrams and understanding that unbalanced forces create acceleration. The direction of the longer arrow is the direction of the acceleration. And so that is still true in this chapter, okay? So centripetal force, centripetal acceleration always point in the same direction. Okay, so the other option that we have here for our equation is actually something that a lot of students would want to make a two-step problem. If we had a situation where the problem gave me the mass of the object, and it gave me the velocity of the object, and it gave me the radius of the circle that the object is following. Now, if they ask us, what is the centripetal force that this object is experiencing? A lot of students are just going to want to jump to F equals ma, which is fine because we need a force. And so this would be a logical equation because F is our unknown. But if we compare the variables that we have to the variables needed in this equation, we see that we have a mass, but we don't have the acceleration. So once you realize that this is the only applicable equation, we have to use this formula. So if we are missing our acceleration, our thought process should be, is that a set number that I should know? The only time we have a set number for acceleration is if it's supposed to be the acceleration due to gravity, and in this case it is not. So then we would need to say, can I calculate that value using a different equation? And so our acceleration equation that we received earlier today is a equals v squared over r. And so if I look at the formula, if I look at the list of givens, I have a velocity, I have a radius, and so I could solve for my acceleration and then plug it in and make it a two-step problem. The other thing that I could do is I could recognize that this equation could simply be modified so that it's mass times, and then we're going to take what acceleration stands for and we're going to put the details in its place. Instead of putting the letter A here, I could simply plug in this information and write that in as the remainder of my formula. Now, for this class, I am going to choose to only give you A equals V squared over R on the formula list and F equals MA. If you must make it a two-step problem, by all means do so. Please remember to use your answer button when you take that acceleration and substitute it into the force equation. But if you are capable of recognizing that you can simply merge the two together and replace acceleration with v squared over r, then you could simply write your own equation like what you see here in the second box. Okay, so I will leave that up to you. Again, v stands for linear or tangent velocity. Sometimes you'll see it as a vt. And r, once again, represents our radius, which we want to have in meters. All right, real quickly, we're just going to look at a conceptual question here. It says the clothes in a washing machine are forced in a circular path, but the water is not. It flies off tangentially. So what this means is that when we put our clothes in the washing machine, that drum turns so that it creates a circle and your clothes get spun round and round. If you've ever opened the washing machine after the cycle is finished, you will see that all your clothes are smushed up against the outside edge of that drum. They're all pressed against the inside of the washing machine drum. The clothes themselves do not exit the drum. Why? Because the wall of the drum serves as a centripetal force that pushes those clothes back in towards the center of the circle. So there's your centripetal force. But these tiny little holes are large enough that allow the water to pass through. Everywhere that there is a hole, if the water hits that part of the drum, well, it actually doesn't hit the drum, it flies out through the hole. And so what we're seeing here in this illustration are all the different paths of the linear or tangent velocity that the water experiences because it does not have a centripetal force acting on it. Okay, so I want to make sure that you understand the difference when things go in a circle and why, when things follow that path of inertia or that tangent velocity and why. When we talk about driving, we've already spoken about forces being responsible for moving objects in class. We've likely already discussed how if we hit a patch of ice, we do not have that frictional force, which would act as the unbalanced net force, which would cause us to turn or change the direction of our vehicle. And so that's basically what we're talking about again here. It says the centripetal force is what holds the car in a curved path. In other words, if we are talking about the frictional force, if that net force, if that frictional force ends up being what is responsible for creating the unbalanced or net force, that frictional force is going to cause my object to turn, and in this case, it's going to create a curved path, which if we just held the wheel so that we were creating that force inward, 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 we would ultimately make a circle, right? So our conversation in previous lessons about the friction between our tires and the road, creating the unbalanced force that causes us to change the direction of our car, aka accelerate, because the direction changed. Now we can relabel that net force and say, oh, we can also call that net force our centripetal force because it is what causes our object to turn, which would ultimately make a circular path if we were to hold that force and keep it directed towards the center. Now, the second picture says if the frictional force is not great enough, or what we would say is if the net force does not cause the acceleration. So in previous conversations, this might be where our patch of ice comes into play where we have no friction for at least a time being. And so at that time, we said we wouldn't be able to control our car. Whatever direction our car was going, it's going to continue in a straight line at that speed because we were focusing on the word inertia. Well, now what I want you to understand is if we do not have a net force that is capable of turning that object or of creating a centripetal force, now my object is going to follow a straight line path. It is no longer going to be curved. It's going to be straight lined. And this would represent the linear or tangent velocity that the object would experience as it follows that path of inertia. So we want you to be able to understand when does the object turn, when does it not. If it does not turn, if it loses that frictional force, if it loses the centripetal force, whatever that situation may be, a ball on a string, a satellite that for some reason is not close enough to be pulled by Earth's gravity, whatever the circumstances, what is the path that it would follow? That is called the linear velocity or the tangent velocity, and we know the path that it's going to travel because of the object's inertia. So make sure that you can interpret these situations and identify your centripetal force, your tangent velocity, and the path the object would follow if it lost that centripetal force, or what it says here, if that centripetal force is simply not strong enough, okay? All right, we're going to recap now. We have talked about linear properties. So my linear variables are going to be located on the left side of our picture here. I have my linear velocity, and I'm going to make this correspond to what we see in the drawing. So our linear or tangent velocity would be this vector here, which shows the object's path of inertia. If it were to leave the circle for some reason, this is the path it would follow at this particular moment. Now, this would imply that the object is moving counterclockwise around our circle, okay? The direction of the acceleration, this is always a centripetal acceleration. So my acceleration here is pointed towards the center of the circle because that's what centripetal means. The force is also a centripetal force. So my force vector is also pointed towards the center of the circle. And the main thing that I want you to get from this illustration is I made the arrows different so that we can tell there were two different vectors pointing towards the center of the circle. As long as we understand that force and acceleration are both directed to the middle of the circle or that axis of rotation for previous quiz and test questions, that's what we're going for, okay? Then we have our angular variables. Remember, angular means around the circle. Angular means curved. So when we look at this new variable, omega, this is going to stand for the curved velocity as the object goes around the circle. So in this illustration, here's my omega, and notice that they drew it as a curved path because this is showing how my object is going around that circle. So my omega is a curved path. It's the velocity around the circle or the curved velocity. And remember, this is measured in radians per second. Then we have our theta. So this last variable on our illustration is theta. This represents the angular displacement, or in the past, we've just called it the angle. And so we talked about how 45 degrees, 90 degrees, follow your hand in the air and imagine that it made a line at the end of your fingertips and you would end up with a curved line. So if we have an object that starts here on the circle and it ends up here on the circle, I cannot take a straight line ruler and say, well, this is how far it traveled, because it did not travel along a straight line path. Instead, I have to measure on the curved route what that displacement is, change in position from beginning to end. And you can see on the picture, that's what we have labeled as our theta. And so this is going to be our angle, or our angular displacement, our displacement around the curve. And this is going to be measured in a new unit called radians, which we often just abbreviate as rad. Now, in previous lessons, we talked about it in degrees. Whoever developed the equation that shows how these variables relate to our angular displacement did not set up the relationship to calculate using a measurement of degrees. Instead, they used a measurement of radians, which is a different way of saying how much of a circle. Okay, so we are going to use the unit of radians, but it is our angle, it is our theta, it is our angular displacement, it is our how far on the curved path. All right. Okay, so there are two more things on these illustrations that are not labeled because they are not technically new variables for us related to our circular motion, but I want to make sure that you know what they are. This right here represents my object. Every object has a mass. Remember, we are quantifying matter, and we're saying how much matter we have by measuring in kilograms. So if you have a question and it talks about the mass, or if we're looking at a picture and we want to know where the object belongs, it's going to be that mass, for lack of a better word, that dot in this particular picture that represents our object that's going around in our circle. The other thing that we have is actually present on both circles because this is just a part of a circle. If we measure from the center of the circle to the edge of the circle, this right here represents our radius. This is just a way of telling me how big or small my circle is, but make sure that you understand radius needs to be measured in meters and is only from the center of the circle to the edge. So if we give you the diameter, we got to cut that in half, okay? Radius, a part of a circle, not a radian, which is a unit, okay? Make sure you know the difference between a variable and a unit. This is the variable radius, and it is measured in meters. And we can see that the radius is also represented on this circle because this is just a property of the circle. This is just part of identifying how large or small our radius is. So R for radius measured in meters.